Alright, so we've been talking about Euler circuits. Remember, Euler circuit is a circuit in the graph which uses every edge exactly one time. As we've seen, there are many graphs which have no Euler circuit. In fact, if you just invent a graph at random, it's probably not going to have an Euler circuit because it's probably going to have some odd degree vertices. So, in such a case, if there is no Euler circuit, what's the next best thing? Like, remember, in a typical, real-world application of Euler circuit, it's something like, let's say Mr. Plow wants to plow all the streets, right? And he lives right here. Can Mr. Plow drive across every street one time by going around these vertices and end up back at home? The answer is no, but you look at the degrees, right? And I see you should be focused on, are they even or odd? And here, there are 4 odds. So this one has no Euler circuit. Remember, Euler circuit requires all even. Which means, in the context of this invented real-world problem, it means that if somebody starts in the middle here and they want to plow every street and end up back in the middle, in this example, it is not possible to do that without repeating some of the edges, right? No Euler circuit means if you want to do a circuit, it must repeat some of the edges. The natural question then, if you were really trying to do something like this in the real world, would be, what's the circuit which has as few edge duplications as possible? Right? Given that we know there is no way to do it with no edge duplications, what's the best? Can you do it, say, by repeating one edge? Or for some reason, do you have to duplicate 2 edges in this example? No. That's what I want to talk about here. So, such a path, this idea here, or such a circuit which has as few edge duplications as possible, such a circuit is called a minimum duplication circuit. Not a very creative name. Minimum duplication circuit. Or I will sometimes write min-dup-circ. Alright? So, today I want to talk about how do you find a minimum duplication circuit in a graph. Euler circuits often do not exist. These would always exist. This just means the best possible way. And I mean, there always is some best possible way to do it, using as few duplications as possible. We'll come back to this example in a little bit. Maybe we'll talk about a much simpler example. Let's try this example right here. Very simple. All right. Let's draw or figure out the degrees. They are 2, 3, 2, 3. So here there is no Euler circuit because I have some odds. Remember, Euler circuit requires all to be even. So I would like to know, can you do a circuit which hits every edge but only repeats one of them? Actually, that is true. To do every edge and only repeat one of them, let's say I want to start at the 2 up here. I can do like this. Come down there. Across, back across, down here, up there, and end up back where I started. So, this right here, this is a minimum duplication circuit. Min-dup-circ. It repeats one edge, right? I went over this edge twice. And how do I know that's the best you can do? Minimum duplication means it's the best. It has the fewest possible duplications. Well, I know that it's not possible to do it with 0 duplications. That would be an Euler circuit, which cannot exist in this graph. And so this one must be the best that you can do. 1 is better than 0. You can't get any better than that. So this is a minimum duplication circuit. How could you find this if you didn't know? Like, this one is small enough that you could probably just figure that out. How could, if you didn't know already how to do this, how could you find a minimum duplication circuit? Here's the idea. Actually, in this example, the one to be duplicated, it must be the one across the middle. Here's the basic idea. you look at the original graph, and we are going to double edges in the original graph to make all degrees even. All right, we'll stick with this example because it's simple. And this actually, as I did that before, I was doing this in my head. A little behind the scenes. I don't know if you care about what I was doing in my head. All right, this was the original graph, which had degrees 2, 3, 2, 3, right? I'm going to use a different color for this. When I look at this graph, I'm going to first identify the odds, right? And you should view the odds as kind of like a problem. If they were all even, then you wouldn't have to do any duplication. So the odds are the ones that you want to worry about. And my basic idea says double edges in the original graph to make all degrees even. By double edge, I mean you look at some of these edges, you don't do it to all of them. Some of them, you're just going to draw like a little clone of that edge, right, going between the same vertices. Think about it. If you do that, if you double up one of those edges, it changes the degrees. Like if I were to double this edge instead of just 1 from the 2 to the 3, what if I just make it so there's 2 now? Now I have increased the degree by 1 on either side because now there's an extra edge that didn't exist before but now hits this one, and also an extra edge. So the degrees now become 3 here and 4 here, all right? And I made this one even, which is good. Like the idea is you want to double edges in the original graph to make all the degrees even. The problem is this one used to be even and now it's odd, so I screwed that one up. I fixed this one, made it even, but I messed that one up. Is there a better way I could have chosen which edges to double? Yes, there is. In this example, you should choose the edge which goes across the middle. If I do that, I'm going to double up this edge. Delete. And now that increases each of these degrees by 1. So this degree is now 4. This degree is now 4. And in my modified graph, now this does have an Euler circuit. This has an Euler circuit. Because now I changed it so that all the degrees are even. All right? This is referred to as the Eulerized graph. All right? What you do to get the Eulerized graph, or to Eulerize a graph, it means you double up some of the original edges, you duplicate them, you clone them in order to make all the degrees even. All right, this is called the Eulerized graph. Anyway, then how do we find the minimum duplication circuit? You find an Euler circuit in the Eulerized graph. So then find an Euler circuit using the method we talked about last time. Fleury's algorithm allows you to find an Euler circuit in any graph, so in particular this one. So forget about the original graph for the moment. I'm going to just consider the Eulerized graph, and I will make a circuit, let's say starting from up here. I'm going to go down like this. Remember the idea about bridges and all that? You can choose whatever you want, only never use a bridge among the edges which have not been used yet. So maybe I'll go down this way, up there. Now I don't want to finish early, so I'll have to go across the middle. And then from there I must go back across the middle. And then finally up there, and I'll be done. All right, this is an Euler circuit in the Eulerized graph. But this one, this circuit, because I didn't create any new edges, I just doubled ones which already existed. This circuit can be translated back to the original graph. The original graph, the OG, that's what that stands for, right? The original graph. This circuit that I drew here on the Eulerized graph can be translated back to the original graph. It's just going to have to repeat this edge. It did this edge twice, which was only one edge in the original graph. So this circuit can be translated back to the original graph, and I'll just say it will repeat some edges. All right, so in this example, back to the original graph, which was that. My circuit, I'm just going to do this same circuit on that graph. And it'll go down here, up there, across the middle, back across the middle, which is a repetition. Over here was two separate edges, but here's an edge repetition, and then back up to the top. All right, and this is the minimum duplication circuit. All right. So this is the idea of finding a minimum duplication circuit. First, you Eulerize the graph by doubling some of the existing edges. You gotta make sure you don't just invent new edges. You don't create new edges where there weren't edges before. You have to double existing edges. That's so that this last part of the process works. You have to be able to translate this onto the original graph. And if you create new edges that never existed, you won't be able to translate it onto the original graph. All right, let's just do some more examples. That's the kind of guy I am. All right, and let's say this is the graph, and your goal would be to find a minimum duplication circuit. Find a min dup circ. All right. You know, the example I just did, I drew like 3 separate pictures. Actually, once you know what you're doing, it's not hard to just do it all on one picture. But I'm gonna separate it out a little bit just so that everything is totally clear. First thing to do is look at the degrees. Maybe it's possible to find an Euler circuit, in which case you don't have to do any extra work. The degrees here are 2, 3, 3, 2, 3, 3, 2, 3, 3, 2, 3, 3, and then 4s on all the inside. Okay, so there's many odds here, which we are going to have to deal with. There's no Euler circuit, definitely. I'm going to kind of circle these odd ones because you should view these odd ones as kind of like the problems which are in need of repair, right? Let's Eulerize first of all. Eulerize. We are going to try to duplicate existing edges in a way which causes all these ones which are odd to become even. Now, the way to do this is you want to think of these odds as if they were in pairs. So try to pair up the odds and then join them by duplications. What I mean by that is I see these 2 3s which are right next to each other. I'm going to duplicate this edge in between those 2 3s. So now there used to be 1 edge, but now there's 2. That causes the degrees here to become 4 and 4, which are both even, so I like it. All right? And I'm going to do that also. I consider these 2 3s together. Why these 2 together? Well, because they're next to each other, and it's convenient to just duplicate an edge that goes right between them. So like that. Now that's a 4, now that's a 4, right? These 2 I'm going to pair up and duplicate that edge. Now that's a 4, now that's a 4. And these 2 I'm going to duplicate this edge. And now this is a 4. And now this is a 4. Okay, so this graph right here is the Eulerized graph. And now we can draw an Euler circuit on this graph with those duplicated edges. And you use the Fleury's algorithm as we talked about last time. I hope you're a Fleury master. Let's start over here, say. It doesn't matter where you start if you're finding Euler circuits. All right, let's just see if we can do it. I'm going to try to kind of go down here, cover everything, and maybe make my way back this way. I don't know. We'll see how it goes. I'm going to go there first. I'll just go all the way across the top first. Okay, and then we'll come down this side. Let's come down here. I'm going to go all the way down. Why not? Around like that. Okay, what's left over here? Remember, when you're doing the Fleury's algorithm, you should always be thinking about looking in your mind at the edges which you did not hit yet. That would be, there's this one, this blue one here plus those 2. There's this blue one here plus those 2. Maybe I'll hit that stuff right now. Come up here, back this way, across the blue guy, and then back like that. All right, now I've covered everything over here, except for this thing. Let's just do that now. I'll go up, across there, and then down like that, and then maybe back here. All right, now I've really hit everything. From here, I must go down there. From here, I must go across there. Okay. What remains to be hit? These guys, this one, these 2, and that stuff. So maybe I'll go down and get these 2 now. From here, I got to go across the bottom. I'm running low on the ink there. It's not really ink, is it? I don't know what it is. Come up here like this. We're almost done here. What's left is this box here, this blue thing, and that last edge. So maybe I'll do that. Get them up there, over there. I got to go down here and back up this one. And finally like that. And I think that does it. I hit every edge, didn't I? Didn't I? I think I did. Now on the original graph, what this looks like is a circuit. I'm going to draw the same circuit again, only it repeats some of the edges, right? It repeats these blue ones. It does those ones twice. So my final answer then would be, sorry I have to, well, maybe I'll draw like a smaller version of my final answer. So in my final answer, the graph, of course, doesn't actually have two edges here. It has only one edge, but I'm going to run across it twice. So starting up here, I can just do this same picture. I went across the top to begin with, then down the right side, all the way down. Then I went around this little square here. I came up across this edge. Then I went up around there. I'm just drawing the same thing again. Up here, over there. Then I came down, back around this way, that way, that way. Down here now. Down here, duplicate that edge, across, up. Then I went across here, up there, over there, down here, back up the same edge, and like that. All right. So this is now my minimum duplication circuit. And I duplicated 4 edges, right? I duplicated 4 edges. Here, 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 and here. They're the same 4 edges that I had to double up in the original picture. Okay, and you can't do it by doubling, by duplicating fewer than 4 edges. You can tell you had to. I mean, I had 8 odds here. That requires at least 4 duplications in order to make them all even. So there's no better possible way to do this without repeating 4 edges. All right. Let's just look at a couple more examples. It is possible these can be slightly more complicated than that, but really not much more. That was about as complicated as these are going to get. How about something like this with a vertex in the middle? Let's do the same thing. Find a minimum duplication circuit. Maybe I'll just draw it on one graph this time. You begin by looking at the degrees. I got 3, 3, 3, 3, and 4 in the middle. So these are the odd ones. And you want to duplicate edges which make which connect up the odds. Now, I think there's 2 ways you could sort of pair these up. You could say this 3 and the 3, they go together, and then these 2 3s go together, or you could do it here and here. Whatever. Let's just do it. Say these 3 go together, so I'm going to create a new edge right there, and I'm also going to create a new edge like there. Remember, you only create edges by duplicating existing ones. You don't invent a new edge which never existed before. Anyway, now that I have this, I can draw in my circuit. I'll do it in this color, which is going to run out, hopefully. Let's start up in the corner here. Again, I didn't say so, so you can start your circuit wherever you want. So I'll go across the top and then back across this. That's one duplication. Come down here, come up here, down like that. Maybe I'll go back up the middle, back down here, over here, and back up. I think that does it. I hit every edge there. I had to do 2 edge duplications. 2 duplications were necessary because I had 4 odds. There's no way to do it any better than with 2 edge duplications. I got another one. Here's one where something slightly more interesting happens. Let's say we got that. We got this, and then we got this. All right, this is like a guy, a sumo wrestler guy with no neck or something. Find a minimum duplication circuit here. Something interesting happens in this example that didn't happen in the other ones. We'll see if you believe me. first you look at all the degrees, fixated on where the odds are. All these intersections are vertices, right? Here's a 3. Okay, so this is interesting because that's a 3. All the evens you care less about. And this is a 3, right? So that one matters. All right, we have one pair of odds. The problem here, what makes this one slightly more interesting, is they're not next to each other, right? So you can't just duplicate the edge from the 3 to the 3 because there is no edge from the 3 to the 3. What you have to do in this case, so I'm going to say if the odds are not adjacent, which is what's happening here, they're not next to each other, so you can't just duplicate whatever edge connects the two odds. You find the shortest path between them and duplicate every edge on the path. Alright, so in this case, the shortest path between them would just go from this 3 straight across to that 3, and I have to duplicate all of those edges. There are 3 of them. So I'm going to duplicate here, and here, and here. Alright, so in this graph, a minimum duplication circuit will require 3 duplications. So here, we need 3 duplications. Alright? Because I had to duplicate those 3 edges. And there is no path between those 2 points which has fewer than 3 edges on it. Alright? Actually, you could have also done down, across, and up. That's also 3 edges. But you can't do it with only 2. One thing to look at, are you concerned that I'm going to mess up the 4s? Remember, when you duplicate one of these edges, you increase the degrees on either side. So when I duplicate this one, this becomes a 4, right? But then this one's going to become a 5. Are you worried about that? It's okay. Everything's going to be fine. Why is it fine? Actually, I also duplicated this one. So this 4, it becomes a 5 because of this extra one. But actually, it becomes a 6 because of this extra one. There are 2 extras. So this 4 becomes a 6. This 4 also becomes a 6. This 3 becomes a 4. And it's all good, right? They're all even now. And so if you wanted to, you could draw in your minimum duplication circuit by finding an Euler circuit in this graph. All right. I don't think we need to go through the actual drawing of the circuit. So typical, homework question or test question about this, I might say, find me a minimum duplication circuit, in which case you actually do have to draw the circuit. Or I might just say, how many duplications are necessary in a minimum duplication circuit? In this case, you can say 3 duplications are necessary, but if I didn't ask you to draw the circuit, then you don't have to draw the circuit. This is a lot easier to just answer that question. How many duplications are necessary? All right, one more example. Here's an example of a graph in which many duplications are necessary. It's not a very big graph, but how about this? Let's do it actually. Find a minimum duplication circuit. As usual, you look at the degrees. This one is a 1, a 2, a 3, a 1, a 2, a 1, right? Concentrate on the odds. Those are the ones that matter. And now you have to join up these odds by duplicating edges. Now, this one is easy enough. I can just duplicate this edge, which makes that a 2 and that a 4. All right, that's great. But I still have these. And unfortunately, the only way to get from this one to that one is to duplicate all of these edges along here. All right, like I always say, you cannot invent a new edge down here because the idea here is you're trying to duplicate existing edges. Don't create new edges. So, unfortunately, we have to duplicate here, and here, and here, and here. That makes this degree 2. This degree will now be 4, because it used to be 2, but I duplicated each of those. This degree, actually, it was 4 after that, but now I just added 2 more. This is now 6. This is now 4. This is now 2. And now this is the Eulerized graph. Actually, in this case, we had to duplicate every single edge. This is like the worst case scenario. Every edge needed to be duplicated. So in this case, we must duplicate, how many? 1, 2, 3, 4, 5. 5 edges. I said find a minimum duplication circuit, so I guess that means you actually need to draw it. So this is the original graph. I'll draw my circuit in yellow. Let's start up here. I'm going to just have to repeat every single edge. So I guess I got to go down here, come back up the same edges, go around here, come back up the same edges, and back to where I started. All right? This is the minimum duplication circuit. Like the wishbone. Grab that thing. Let's try it. I want you guys to try some examples. See what you think. How about these ones? Two separate examples. Find a minimum duplication circuit in that one. And how about, I got this one. All right. Find a minimum duplication circuit in that one. See what you think. Busy. Did you get them? Let's talk about it. So this one, you begin by looking at the degrees. And you see two odds. You should duplicate this edge, connecting up those two odds. And then your circuit just has to go across that edge in the middle twice. It should look like, if I'm going to start here, say. I mean, there's many ways you could do it, but here's one way. Like that, right? So that's a minimum duplication circuit. It requires one edge duplication. What'd you say for this one? Well, the degrees this time are a 3 there, a 3 there, a 3 there, a 3 there, and a 2 there, right? There are 4 3s. I'm going to have to duplicate at least 2 edges. Can you pair them off so that like 2 are matched and then the other 2 are matched? I think you can. I'm going to, so there are these edges, right? Or these vertices are the problems. I'm going to add an edge there and also add an edge there. So when I draw my circuit here, it's going to duplicate that edge and it's also going to duplicate that edge. Let's see if I can make it happen. Let's just start here, say. I'm going to go, so this is the one edge I'm going to duplicate and that one also. All right. Maybe I'll just immediately come back here just to make sure I hit that one twice like I have to. Then I'll go around this way maybe, down here, up there, and I guess I'll have to come around this one twice. Like so. All right. I duplicated those 2 edges and hit all the other ones. Okay, so this one requires 1 duplication. This one requires 2 dupes. All right, excellent. One last thing I want to say about this topic is you can also do the same thing for paths. These are called minimum duplication paths. What's the difference between minimum duplication circuits versus path? Well, path just means it does not start and end at the same point. And when you're finding minimum duplication paths, I'm just going to say you do the same thing, but you can leave 2 vertices as odd. Remember, to find an Euler circuit, they all must be even. But to find an Euler path, where it starts and ends at 2 different places, to find a path, they all got to be even except for 2 odds. So when you do the Eulerizing process, if you're looking for a minimum duplication path, you should do the same thing, but leave 2 of the vertices as odds. Let's just do one example like that. I think you will know what I mean. All right, this is my example. Let's say this is your graph, and you want to find a minimum duplication path. This is sometimes referred to as an optimal parade route. That's because, like the parade, if this was say a city block neighborhood, you want the parade to go down every street, right? So that every little kid can see the Mickey Mouse balloon or whatever it is. You want the parade to hit every street. You don't really want the parade to repeat any more streets than it really needs to in order to hit every street. So this minimum duplication path, sometimes called an optimal parade route. You can start and finish wherever you want. That's part of your job, is to figure out where's the best place to start, where's the best place to finish in order to make the fewest possible number of repetitions. Anyway, we do the same old thing, which is begin by looking at the degrees with an eye out for odd degrees. So the odd degrees are, there's a bunch of 3s here, right? Those are all odds. This is a 2, which is not. That's a 3, which is odd. This is a 4, that's okay. That's a 2. That's a 4. That's a 3. All right, that's an odd. That's a 3. That's odd. That's a 2. That's a 3. It's odd. That's a 3. It's odd. That's a 3. I got a lot of odds here. Here we got 5. Okay. Here we got 5. Here we got 5. Here we got 4, 4, and 4. And I think I looked at all of them. So the circled ones are the odds. What you would like to do is somehow pair up the odds, join them together in order to turn them all even. And remember, since I said minimum duplication path, it means we're going to Eulerize in the usual way, but we can leave 2 odds. All right? Eulerize, but we can leave 2 of them as being odd. So when you look at this, you should ask yourself, which of these 2 do I want to leave as odd, and then I'm going to try and pair up all the other ones? Well, actually, I am immediately drawn to these 2 here. They cannot be easily paired up at all because they're not next to each other. This one is next to that one, so you could pair this one with that one, but then this one would be all kind of stuck. So my idea when I just looking at this first is I'm going to leave these 2 as odd, and then I'm going to try and pair everything else up. So leaving those 2 alone, can we pair the rest up by just duplicating individual edges? Well, I think we probably can. So let's put these 2 together. I'm going to duplicate there. Now I just have these left over, and maybe I can duplicate here, 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 and here, right? Okay, so how many new edges was that? I should have done these maybe in another color so we can see. 1, 2, 3, 4, 5 duplications, all right? So in this case, the minimum duplication path, I'll just say will require 5 duplications. That means the parade has to go down streets it had already visited 5 times, actually. And the parade should start and end at these 2 vertices. One should be the start, the other should be the end. All right? Now, I said find the minimum duplication path. Let's see if we can actually draw it in there. I'll just use another color. Okay, let's start at this one. Now it's all muddy. All right, we're just going to cover everything. Hopefully, we'll end up at this other 3 if we do it correctly. All right, let's do it. All right, I'm going to come up this way. Now I have to go down here. Remember, I'm doing Fleury's algorithm, which means in your head you should be keeping the, hold in your mind the set of all the edges that you did not yet hit, and you want to make sure that that stays all together in one connected piece. You never disconnect the ones you didn't get to. So I'm doing fine so far. All the ones I didn't do are like down here in one grouping. Let's just go. I'm just going to kind of try and eat away at the rest of the graph gradually here. Go down there, come up here, go across that way. I better go down here. Maybe I'll come across. I'll hit these 2 guys, right? Better go down, over. Okay, how am I doing so far? I think pretty good. All the edges I need to hit are like over here and up there. All right. Let's hit this duplication there, and I'll go across. Maybe hit this duplication. Come up there, go down this way. Maybe hit this duplication. How am I doing now? I have a triangle here that I still need to do, plus stuff up here. I'm going to go get that triangle right away. And maybe come back across this way, up here. Am I doing good? 3. This 3 is where I'm going to finish, so I think I should be in good shape here. Yeah, there we go. All right, this is the minimum duplication path for this graph. Same idea, just leave 2 of them as odd. All right, we still got a little time here. I'm going to just give you a little introduction to the next major topic. Everything we've been talking about the past few times has been about Euler circuits. There's another type of circuit. Euler circuit uses every edge one time with no edge repetitions. It is natural to ask, what about using every vertex one time with no vertex repetitions? There's a name for that too, and that's named after a different person. That's called a Hamilton circuit. This is named after the mathematician Sir William Rowan Hamilton, not the American politician Hamilton circuit, not the American Alexander Hamilton. Although, little known fact, there is a mathematical concept named after Alexander Hamilton. This guy Hamilton is a famous mathematician. Many things are named after him, but there's something that Alexander Hamilton invented, which is called the Hamilton apportionment algorithm, which is something that is used in the for deciding how many representatives people get in the Congress, or something like that. Anyway, this is not that Hamilton. The other Hamilton. Hamilton, the mathematician. Hamilton circuit. This is a circuit which uses each vertex exactly once. So, vertex rather than edge. If it's edge, that's a Euler circuit, which we've talked about already. If it's vertex, that's a Hamilton circuit. And it turns out Hamilton circuits are quite a bit more complicated to find than Euler circuits. Euler circuits, it's very easy to say if there is an Euler circuit or not. You just look at all the degrees. And then once you know if there is one or not, it's not so hard to find one using the Fleury's algorithm. In the case of Hamilton circuits, there are not nice theorems and algorithms about Hamilton circuits in the way that there is about Euler circuits. But I just thought, for now, we're not going to get into all that. Let's just look at some very simple examples. So, for instance, what if I have this graph here? From a certain point of view, Hamilton circuits are simpler. Is there a Hamilton circuit? That is a circuit in the graph which hits every vertex once, and you don't care about the edges. You can repeat edges. Actually, you can't repeat edges because if you repeated an edge, you would automatically repeat a vertex. But you can certainly miss edges. There can be some edges that you just don't hit at all. You just got to hit every vertex once. Can you do it? Do you see how to do it? I think actually it's kind of obvious if you're looking for the right thing. Can I hit every vertex once? Yeah. If I start, say here, I can just go around, right? You might say, well, you missed the edge. Doesn't matter. Hamilton circuit is about hitting every vertex once. Missing an edge is not important. For a Hamilton circuit, you don't care about the edges at all. I mean, you have to follow the edges, but if there are extra edges that you don't hit, don't matter. All right? So, this is a Hamilton circuit. The answer is yes. There is a Hamilton circuit, and that's it. How about another example? How about this? Is there a Hamilton circuit? The answer is again yes. Anybody? Can you see how to do this? It's not so hard if you take a gander. Let's say starting from here, you got to hit every vertex, right? Now there are vertices all around the edge, and then there's also the one in the middle. So I'm basically going to go around the edge, but at some point I got to go in, hit the one in the middle, and then come back out. And there is this convenient little diagonal which makes it possible to do that. Like so, that's a Hamilton circuit, right? So this, again, has a Hamilton circuit. All right. What about this? How about same thing, but without that extra diagonal? You should probably feel like this one probably does not. If you think about it, you're going to have to go and hit all these vertices around the edge, but if you actually go around the edge, you will have missed the one in the middle. What if you do hit the one in the middle? Then you'll have to come back out, and it seems like you're probably going to miss one of the ones around the outside. So can I just say this one has no Hamilton circuit? It's really true. This has no Hamilton circuit. But let me just say in parentheses, maybe hard to say exactly why. Although this is something we're going to talk about next time. Can you explain to me why precisely you know for sure that this doesn't have a Hamilton circuit? It's not so obvious, but once you learn a few simple tricks, actually this is an easy case to deal with. How about, here's one that definitely does not have a Hamilton circuit. How about this? This is a weird looking graph. I have 2 points over here, 4 points over here, and every one of these over here is connected to every one of these over here. So it's like that, right? There's actually a name, this is a famous type of graph in mathematics. This is called a bipartite graph because it has 2 parts. There's these 2, and then there's these 4, and then they're just connected in every possible way from here to here, but you don't connect any ones within their own side. Bipartite graph. Anyway, is there a Hamilton circuit here? This one there is not, and it's not so hard to say why, actually. So this one has no Hamilton circuit. How do you know there's no Hamilton circuit? You have to think about this in terms of using the edges. The edges always go back and forth between these 2 and these 4. Now, if you really made a circuit that hit every vertex, it would have to go over here to hit one of these, back here to hit one of these, over here to hit one of these, back here to hit one of these. I still have missed one of these though, but then I have to go back across, and there's nowhere for me to go without repeating these vertices. So can I just say, in order to make to hit every vertex, you must go back and forth at least 4 times, right? Because there's 4 on this side, so you're gonna have to go, back and forth once, and then again, and then again. And then one last time to make the full circuit, right, to get all the way back. So you have to go back and forth at least 4 times, but that's not going to work because that will require you to repeat some of those ones on the right. So we must repeat verts on the right. And this is not allowed in a Hamilton circuit, so there can't be a Hamilton circuit. All right. This is a little tricky. I mean, you have to think about back and forth or whatever. So what we're going to do next time is talk about some general ideas, general strategies, which will work to tell you if there is or is not a Hamilton circuit. There is no simple rule about it, though. Like Euler circuits about all the degrees being even, nothing that simple is going to be true of Hamilton circuits. So a little more interesting, perhaps. All right. See you then.